Hello, my name is Gary Millette. I will be a professor for ELE 240, Sensor Interfacing and Data Acquisition for the fall 2022 semester. Today, we live in kind of exciting times for electronics in that we are in the age of the Industry 4.0, it's called, the age of the Internet of Things. And recently, people have started to talk about the Industrial Internet of Things era. So none of these are possible without data acquisition or using sensors to acquire that data. So this course is kind of devoted to the electronics of how we take and implement Internet of Things applications. I'm going to start the course by introducing modern control systems. Some of the topics we'll consider will be open and closed loop systems, controllers, actuators, set point, feedback, transfer function, digital control, and robotics. That'll be during the first week. During the second week, the basics of embedded control will be discussed. For modern control systems, embedded control is what allows us to expand the use of this technology. Microcontrollers have become extremely powerful, and they're very inexpensive today. Thus, the ability to build electronic control systems into everyday consumer products, like for instance, a microwave oven, has become commonplace and only adds an incremental cost to the product. This week, we'll look at how those devices work and how information is represented in binary. During our third week of the course, we'll have a discussion of embedded control that would continue with real-world examples of microcontrollers. Additionally, the topic of transforming data from analog to digital world and back is discussed with examples of the operation of A to D converters and D to A converters. During the fourth week of the course, you'll be introduced to basic Arduino and Raspberry Pi hardware. An additional topic for the week will be Tinkercad, which is a free circuit simulation software from Autodesk. And then kind of switch gears. In week 5, we will take a look at Control Systems 3.0. These are typically today known as cyber-physical systems. So cyber-physical systems are control systems that are closely or tightly coupled to the physical system that's being controlled. In other words, control of the physical system happens in real time. An example of this would be a modern electronic fuel injection system for a car. Cyber-physical systems are being envisioned for many future applications, from autonomous cars to e-healthcare. And to accomplish this feat of creating a cyber-physical system, we usually incorporate an Internet of Things application. With that, we shift gears again, and we start in week number 6 to look at the very useful electronic tool called the op-amp. So op-amps are ICs that can do a variety of signal processing functions. Most sensors, as it turns out, do not put out a signal that's compatible with a microcontroller. A microphone might only put out microvolts or millivolts. Other sensors might put out large values of voltage. So the output voltage of a sensor is typically either too small or limited in power. Furthermore, the sensor might not even put out a voltage, but instead some other type of electrical parameter might change out of the sensor. For instance, its resistance, capacitance, or inductance. The op-amp is a useful device that can transform the sensor output to the correct electrical parameter and the correct magnitude signal. We continue in week 7 and 8 and 9 by looking at applications of op-amps. Some of those applications will be as amplifiers, summers, adders, integrators and differentiators, filters, instrumentation amplifiers, isolation amplifiers, and so on and so forth. Some of the other things they do, constant current sources, current to voltage converters, or voltage to current converters, and so on. I'll also talk about, their characteristics, things like common mode rejection ratio, and so on and so forth. So after we finished all that, we kind of shift gears again, and in week 10, towards the last third of the course, we start to discuss characteristics of mechanical systems. And since we use electronic control systems to control various mechanical systems, it seems appropriate to take a look at the characteristics of mechanical systems and the devices used to enable these systems. So topics will include things like friction, bearings, springs, mass and inertia for both linear and rotating systems, levers, energy, heat transfer, mechanical resonance, gears, clutches, and brakes, drive belts, and roller chains. Very mechanical in nature, to say the least. During week 11, we'll take a look at the ever-expanding world of sensors. Topics covered will include position sensors, rotary position sensors, LVDT sensors, tachometers, proximity sensors, load sensors, force sensors, pressure sensors, temperature sensors, flow sensors, liquid level sensors, vision sensors, and then we'll delve into the world of MEMS and NEMS. MEMS are micro electromechanical systems, and NEMS are nano electrical mechanical systems. We've been able to take and create sensors that heretofore we could not create in the past, and this opens up a whole arena of new applications. During week 12, we take a quick look at the enabling technology of wireless networking. Some of the topics covered are cellular networks and the IEEE 802 technologies, specifically 802.11, which is Wi-Fi, 802.15, Bluetooth or Zigbee, whatever you want to call it, and some of the more newly emerging wireless technologies like LoRa or long range wireless. Week 13, we turn our attention to the workhorses of mechanical systems, which are motors. After an introduction to the fundamentals of DC and AC motors, stepper motors are introduced. An overview of stepper motor operation and control is presented during that week. When we move on to the last couple weeks of the semester, week number 14 will be control system actuators, and they're either electrical, we already mentioned motors, hydraulic, or pneumatic. So we'll cover those topics. Then during the last week of the course, we kind of return back to the first week topic, feedback control systems. And after a quick review, we shift our attention to today's modern systems that are proportional, integral, and derivative, or PID control systems, and some variations of that architecture. Should be a fun course. The lab that goes with it will have a lot of hands-on activities, and I look forward to working with you this semester. Thank you.